Assalamu alaikum. This is Discrete Homotopy Theory lecture series. So our topic is homotopy groups of graphs. Homotopy groups of graphs. Okay. So we saw in previous lecture the definition of path homotopy between paths. Okay. For finite path or infinite path, let's say recall from IM box product with I1 to this graph M path graph x0 to x1 such that h dash comma 0 we will get gamma and h dash comma 1 we will get sigma. So we can say gamma is adjacent to sigma. Okay, or we can say gamma is homotopic path homotopic a path homotopic to sigma for finite length. Or if we introduce in infinite length, so the graph, there exists a graph map from IM box product with I infinity to BM x comma x naught comma x1 such that if there is a condition if there exists n minus n plus belongs to integers. Okay, I'm recalling the previous definition, then I will explain new topic. So there exist two integers n minus and n plus. If we substitute h dash comma I is equal to gamma for all, if for all I is less than n minus, and h dash I comma h dash comma I is equal to sigma, if for all I is greater than or equal to n plus. So we can say gamma and sigma are path homotopic and adjacent in this graph. Okay, so there is a path homotopy between these two paths. Okay, so let's study the new definition and discrete homotopy theory definition. So for a pointed graph, we have a pointed graph. What is pointed graph? X comma x naught. We have x naught base point. This is like a base point x naught, and m belongs to natural number union infinity. Means either m is finite or infinite. The m loop graph omega m x naught comma x naught. So what is this type of graph? Means m omega m x naught to x naught. Means this is a graph. And what type of graph? This is a loop graph. What type of loops? Omega i's from x naught to x naught, starting and ending point x naught. And what type of map? This is a map im to x, such that if we substitute 0 we will get x naught, and if we substitute m we will get x naught. Means x naught is a loop, gamma is a loop from x naught to x naught. For m length, all the loops in this graph are vertices from x naught to x naught. Okay, m length. And what is the edges? There exists a homotopy, graph homotopy, path homotopy. This is a graph map. IM box product with I1 to x such that h dash comma 0 we will get gamma, and h dash comma 1 we will get h dash comma 0 we will get x naught, and this is a graph map. H dash comma 0 we will gamma, and h dash comma 0 1 we will sigma. And if we substitute h 0 comma I is equal to x naught, and if we m comma I, we will get again x naught. Means these all the maps based at x naught. Okay, and all the maps based at x naught are the vertices of this loop graph, and edges are homotopies, one step of homotopy. Okay, from one path to another path. So this is here is a loop graph omega m x naught comma x naught is given by is given by is given by is given by the m path graph pm. You saw this graph in previous lecture. All the loops from im to x such that gamma 0 is equal to x naught and gamma of m is equal to x naught means starting from x naught to end at x naught means initial and final point are same. So this is the loops. So the m loop graph is given by this graph. It has a distinguished vertex. It has a distinguished vertex. It has a distinguished vertex. Distinguished vertex given by the constant path. Given by the constant path at x naught. Okay. Given by the constant path at x naught of length m, whose length is m. This gives an endofunctor. Okay, this gives an endofunctor. Oh, wow, what is endofunctor? First of all, we have to know okay, what is functor, then what type of endofunctor. So endofunctor omega m from the category of graph with base point pointed graphs to the category of pointed graphs. Okay. So what type of endofunctor, and then iterating endofunctor, we can iterating iterating the endofunctor. How can we iterate endofunctor? First of all, we will see the functor endofunctor and how can we prove this is a functor, prove functoriality. So let's see. So endofunctor, what is the definition of endofunctor? First of all, recall the definition of functor. Functor is a morphism from one category to another category. Send every object to the object in other category. Mean f of x is an object in D for all x belongs to sorry, for all this is H category, for all x belongs to G category. Okay, and for every morphism ff from fx to fy, from this morphism get from the morphism x f from x to y. Okay, means the functor sent every object to the object in another category and every morphism to send to morphism between the objects, which is the images of previous objects. So functors send morphism to morphism and objects to objects, mean preserve the structure. Okay, and the condition of functoriality axioms means preserve composition, means f of g of f is should be equal to f of g compose f of f, and f of id on x should be equal to id on f of x. Okay, this is the functoriality axiom. So let's define the endofunctor. What is endofunctor? What is endofunctor? So endofunctor is a functor from same category to same category. Okay, from category C to category C. Object x to f of x belongs to the objects of C category, and f of x belongs to the objects of C category. And morphism, let's say f is a morphism from x to y in C category. So f sent to ff, which is the morphism in category C. Okay. So endofunctor defines from C category to C category, same object to the object in C category, and same morphism in object C to morphism in C category. Okay. So let's prove the endofunctor, this type of endofunctor from category of graph with pointed graphs to category of pointed graphs. So how can we define this is the functor? Okay. So let's say x comma x naught is a object in this category. This is a pointed graph. Omega m. This functor sent to a graph, pointed graph with base point. So okay, this is a graph and this is a base point. And here we can see this is the graph whose vertices are morphism from x naught to x naught. Okay, and edges are path homotopy between one path to another path, one step homotopy, or we can say an step homotopy. And this is the base point here. Okay, this is the base point here, we can say, means cx naught is a constant path from im to x, such that cx naught of I is equal to x naught for all I belongs to in. Okay, means all the i's sent to x naught, so we can say this is the constant path at x naught. Okay, this is the base point here. Then we have a morphism from x naught to x comma x naught to y comma y naught, which is called f, we can say f, and there is a morphism. So there is a f sent endofunctor omega m sent y comma y naught to omega m y comma y naught comma c y naught. Okay, this is base point and this is the graph. Okay, we can say. So where will send f omega m? So omega m send at omega m of f. This is the morphism from this graph to this graph. So define this morphism. What type of morphism we have? So let's define. So let's define the morphism. First of all, again, I draw the picture and diagram also. We have a morphism, this is a morphism, and in the category of graph, we x comma x naught to y comma y naught f, and send x comma x naught to omega m x comma x naught comma c x naught, and y send omega m y comma y naught comma c y naught. Okay, so there is a morphism omega of f. Okay, so we can see there. This is a graph whose vertices are morphism from x naught to x naught. Let's say G is a morphism belongs to this. Okay. Sorry. Let's say gamma is a morphism belongs to this graph. Means gamma is a morphism from im to x such that omega of 0 is gamma of 0 is equal to x naught and gamma of 1 is equal to also x naught. Okay. So let's say gamma is a morphism from x naught to x naught. So where omega m of f sent this morphism gamma. This sent to f of gamma. Okay. What is f of gamma? F of gamma is a morphism from x, f of x naught, comma, f of x naught to f of x naught. As we know, this is the function, this is the graph homomorphism. We sent base point f of x naught to base point y naught, where y naught is a base point in y graph. Okay. So F is a morphism. Sorry, omega mf is a morphism. Send the object gamma to send f of gamma. What is f of gamma? F compose gamma is a morphism from f of x naught to f of x naught, where f of x naught, as we know, f of x naught. What is f of x naught? F of x naught is y naught to y naught. Okay, this is uh, this type of assignment from omega m of f. Okay, means if we let sigma from omega m x comma x naught, omega m f send sigma to f of sigma. Okay, so let's prove the functoriality axiom. Let's prove the functoriality axioms. Then we can say omega m and the functor is a functor. Okay, let's do first of all composition, preserve composition. So first of all, we have a map from x comma x naught, x comma x naught to y comma y naught. Then again we have a morphism from y comma y naught to z comma z naught. This is a morphism f, and we call this morphism G. X comma x naught send omega m comma x naught m x comma x naught to cx naught. This is, and y sent to omega m y comma y naught comma c y naught, and then this object sent to omega m z comma z naught comma c z naught. So this morphism we can say omega m of f, and this morphism is omega m of g. Okay, so we have to prove the composition. What type of composition morphism? Omega g of f is equal to, should be equal to omega m of g compose omega m of f. Okay, we have to show this equality. First of all, so let's say gamma is a path, gamma is a vertex in this graph. So substitute in this morphism. So omega m g of f of gamma, according to the definition, g of f compose gamma. Okay, we get this. This belongs to this graph. Okay, means this is a morphism from z naught to z naught. Okay, means this is a morphism from z naught to z naught. let's let's do it for this right hand side. So omega m of g compose omega m of f. Let's say gamma is a path from belongs to this graph omega m x comma x naught comma c x naught. Okay, this is a graph. You can see this is a graph. What type of graph? Whose vertices are the path m length path from x naught to x naught, and cx naught is a base point. Okay, we can see cx naught is a base point, which is x naught. Means cx naught is a constant path from im to x, which all send all the points at x naught. So cx naught is equal to x naught. So this is a graph. Okay, so this is the vertex. So substitute in this graph, in this morphism. So omega m of g compose omega m of f of gamma. So let's apply this part. So omega mg compose, we will get from this part f of gamma, then apply this part. So we will get g of f of gamma. So according to the category axiom, so we can apply associative law. So g of f is equal to g of f is of gamma. Okay, so this proves shared composition proposition. Now we see the identity morphism, identity preserve, and preserve identity morphism. So let's say x comma x naught is a graph, pointed graph to x comma x naught. Okay, and there is a morphism identity of x comma x naught. So this send to omega m comma x naught comma cx naught, and omega m send x comma x naught to x comma x naught comma cx naught. Okay, so omega m send this morphism to omega m of id on x comma x naught. Okay, and if we forget this morphism, so what is the identity morphism for this object? So id on omega m of x comma x naught comma c of x naught. We have to prove these two morphisms are same, means this identity morphism same to this identity morphism. So apply omega m of id on x comma x naught. So let's say gamma is a path belongs to this graph. So apply in this id on id morphism. So we will get id on x comma x naught compose gamma. So we will get gamma. Okay, so we will get gamma. Now apply this path, and now apply right left hand side. So id on omega m x comma x naught of gamma. So apply identity, so we will get gamma. So proved the omega m endofunctor is a functor because it preserves identity morphism and it preserves composition. So we can say the omega m is a functor. Omega m is the endofunctor. Why endofunctor? Because it send from category of graph to category of graph. So which type of graphs? From pointed graph to pointed graph. Okay, so how can we see this is iterating functor? If we take the x comma x naught, then apply omega m x comma x naught comma c x naught, then apply again omega m of this omega m x comma x naught comma cx naught. So we can say omega m power 2 x comma x naught comma cx naught. Then if we apply again omega m, so again we increase the power of omega 3 x comma x naught comma cx naught. If we apply d times, so we can say omega m x comma x naught comma cx naught. Means what is d belongs to natural number, means omega apply d times. Okay, means we can write omega m compose omega m and how many times omega m apply d times apply on the graph this. So we can say, okay, this is the iteration d times. Okay, so let's end this video. Allah Hafiz. I will explain next topic in next videos. Please share and subscribe my channel. Allah Hafiz.